What you know about the atomic model? Today, we're going to teach you about how the atomic model came to be known as it is today. Tell them, Geraldine.
Dalton, Rutherford, Heisenberg, Bohr, and Thomson. Did I say that twice?
That's perfect. What are we going to tell them about? Why are these people important?
Well, each of their experiments contributed to how we understand the atomic model today.
See, she knows what's good. You're going to walk away, and you're going to have some serious-ass knowledge on chemistry. Some next-level knowledge on chemistry.
So, I was wondering if you can help me learn more about Dalton's experiment. I'm a little bit confused by it.
Of course, this is only natural. Well, in 1803, J.J. Dalton was a seasoned meteorologist who wondered how water and air particles can occupy the same space. So, he reasoned that evaporation must be the mixing of air and water particles. After experimenting, he came to the hypothesis that particles making up different gases must be different.
Okay.
So, in making his atomic model theory, he made 5 assumptions. Number 1, all matter consists of tiny particles called atoms. Okay. Number 2, atoms are indestructible and interchangeable. This is not true because, in chemical reactions, atoms can form different compounds with other atoms, but they can't be destroyed because of the law of conservation of matter. Number 3, elements are characterized by the mass of their atoms, but this is also not true because of isotopes, which are different ratios between protons and neutrons. You getting all this, Kevin? Okay. Number 4, when elements react, their atoms combine in simple whole number ratios. This basically just means that when they combine, their atomic mass is just really just the ratio of those 2 atoms, pretty much. I mean, it was a really simple theory, and critics of his theory were really impressed by the simplicity of this idea.
Okay.
And then number 5, he also, going off on his previous assumption, sometimes these atoms form more than one ratio. This explains why the reactions in atoms are just multiples of the original atom, like their weights. Do you have all this down, Kevin? Yep. All right. That's pretty much it.
That's it? No.
Yep.
What I want to know is, he clearly contributed to the development of the atomic model. What did his exactly look like?
Well, with all of these assumptions, he led to the belief that atoms are just solid, indestructible balls. Just solid spheres. So
just solid spheres?
Yes, unable to be broken apart.
Spheres. Okay, so that makes sense.
Yep, that
awesome.
does.
Thank you very much.
You're welcome.
I didn't type anything.
Welcome to AtomMealTime.com. Today, we're going to be making some plum puddings. Now, I bet you're asking, you're going, hey, Kevin, what's a plum pudding? Let me drop some knowledge on you. Plum pudding is the idea that Thomson came up with in about 1897 about how an atom looked like. Now, the reason it's called plum pudding is because we got pudding, which is positively charged, just like that. With some plums, which are the negatively charged particles, or as we know them, electrons. Now, don't try this at home, I'm a professional idiot. Now, see, spread it out a bit, throw some plums in there, and look at that. Perfect example of plum pudding. Now, this wasn't exactly accurate because, well, we all know what an atom looks like today, but it was still a really good idea, or hypothesis, excuse me, for the time being, because it generated a lot of speculation and more study into the structure of an atom. And The reason he came up with this idea is because using his cathode rays, he discovered that electricity is the flow of the electrons. Particle, and they would leave the atom, and that's how he came up to this conclusion.
Okay.
Maybe keep the camera up. Can you keep it the other way? Because I don't know how that's going to affect.
Okay.
Yeah.
Zoom. Zoom. Okay, now zoom out. Alright, now start eating.
I'm good.
It's really great, Kevin. You look so good with all that on your face. So, in 1918, Ernest Rutherford made yet another important contribution to the atomic model. With Niels Bohr, who created the solar system model, he conducted an experiment in which he threw positively charged alpha particles at hydrogen gas, whereas before he threw positively charged particles at the thin piece of gold foil. So with this new experiment, he saw that the protons, that the particles would hit the protons and the hydrogen, the nucleus and the hydrogen gas, and that they would smash apart, and then a whole bunch of hydrogen nuclei would break apart. So he reasoned that there must be something holding the nucleus together. So in addition to the positively charged protons, there must also be a neutrally charged neutrons holding the whole thing together and preventing it from breaking apart. So later on, James Chadwick, who was a British physicist, actually went off of Rutherford's theory and discovered that there were actually neutrons in addition to positively charged protons, holding the whole thing together and preventing it from breaking apart. So with this information, Rutherford created the proton model. So, in 1911, Ernest Rutherford decided to investigate the atom further. He did this with an experiment in which he shot positively charged alpha particles through a thin piece of gold foil. With the knowledge at the time, it was expected that the particles would just go straight through, because Thomson's plum pudding model reasoned that it was just mostly empty space. So, with this, shooting the particles, he actually noticed that the particles would deflect at a really wide angle. So he thought that there must be a small, dense, positively charged center positively charged center surrounded by negative electrons, and this is why the positively charged particles would hit the nucleus, which is positively charged, and hit at such a wide angle, because they're moving with such a force and they're both like charges. So with this information, he led to his proton model, which reasons that the atom is made of mostly empty space surrounded by negative electrons and a positive nucleus. Done.
All right.
Are you ready to be assaulted? Okay. All right.
Lay it on me.
Notice how some of the particles go straight through the atom, but some of them hit the center. I'm really bad at this. But some of them hit the center, which is positive.
Ready?
Yep. Whenever you want to stop.
That was kind of fun.
I really hope this works. Oh my, okay. I hope none of us gets like maimed.
Gonna set your house on fire. Oh, okay, it's still going orange.
Yeah. Thompson's, Dalton's, Rutherford's experiments, you see that there's a small, dense nucleus composed of positively charged protons and neutrally charged neutrons, which is very small and is surrounded by mostly empty space and with electrons circling the nucleus in specific rings, which are specific distances from the nucleus.
And as we see here, this is an oxygen atom, and it is represented by this on the periodic table. Now, the atomic number is in the upper left-hand corner, which is 8. The atomic number tells you how many protons are in an atom of that specific element, and it also tells you the amount of electrons if the atom is neutrally charged. So we can see here that we have protons are red, so 1, 2, 3, 4, 5, 6, 7, 8. 8 protons. Electrons, 1, 2, 3, 4, 5, 6, 7, 8. So that's a neutrally charged oxygen atom right there. Now, the atomic mass is 15.99, but we round that up to 16. The reason it isn't exactly 16 is because there are isotopes, which are forms of elements but with different amounts of neutrons, which gives it the average, which brings it to a decimal. But we like to round that up to 16 and say there's 16, we're pretty much saying there's 16 atoms in the nucleus. So we know we have 8 protons, and if the atomic mass is 16, you subtract those 8 protons from it, and that tells you how many neutrons are in the nucleus. And 16 minus 8 is 8, so 1, 2, 3, 4, 5, 6, 7, 8. Well, looks like we got a working oxygen atom there, Geraldine.
Appears so, Kevin.
Indeed.
Indeed. Alright, so was that good?
I think so. Wait. Next time, we eat the Big Bang.